gases, this first slide is just properties of gases. So these are pretty basic. A gas has neither a definite shape nor a definite volume. So whatever container you put a gas in is going to take the shape and the volume of that container. And it will expand to fill the entire container that it occupies. Gases always form homogeneous mixtures. That's a good review word for the final. What does homogeneous mean? Give me an example of a homogeneous solution. What? Salt water. But water is not a solution or a mixture, right? Water is a compound. Okay. Remember elements, compounds, mixtures? Okay. Water is a compound because those atoms are bonded together. But in a mixture, you have multiple compounds or multiple elements that are not bonded together. And gases always form homogeneous mixtures, which means they mix evenly. What's the opposite of that? Heterogeneous. And what's an example of that? Good. Sand and water. Chocolate chip cookies, salad, mud. Okay. So things that do not mix evenly would be heterogeneous. Gases have low density. Also, lots to review here. What is density? Okay, good. They are highly compressible, which means if you squish them in, they will change their volume, and they exert a pressure, which is what we're going to focus on for a few minutes here. Okay, pressure. So what is pressure? Pressure is force divided by area. Force divided by area. So if the area is big, then the pressure would be small. Good. But if the area is small, then the pressure is large. So if you take your hand and push on your arm as hard as you can, it's going to feel very differently than if you take your fingernail and press on your arm. Because your fingernail has a tiny area. So that's going to create much more pressure. So what they're trying to work on, like just as a science advancement, is they're trying to make diamonds that have the tiniest tip on them so that they can create really, really high pressure, because diamonds won't break easily. So they could take a diamond-tipped, you can make a diamond-tipped screwdriver. That's a little extreme. But it could handle a lot of pressure. So at UAB, they're creating diamonds like artificially for that purpose. They're not as pretty, so no one wants to wear them on their hands. But in a gas, the pressure is not coming from the gas pushing. Okay, the pressure is coming from the gas bouncing off the surface. And this is kind of the key to this whole section. Underline, highlight, whatever. How do gases make pressure? They make pressure by bouncing off the surface. So how can we make a gas bounce off the surface more? Heat it up. Good, because it's going to move faster. Okay, so it's going to hit the surface more. Think about yesterday in the lab. How else could you make a gas hit the surface more? Very good. Make the box smaller, right? And they don't have as much room to move around, so they'll hit the walls more often there as well. So in a gas, that gas exerts pressure in all directions. So on you right now, there are millions of gas particles hitting you and exerting some pressure. Okay? And that pressure is exerted in every single direction. In a container, there's pressure on the inside of the container and on the outside of the container. So if you have your bottle right there with water, for example, there's gases inside that bottle and outside that bottle, and the gases inside are hitting and pushing out, and the gases outside are hitting and pushing in. And currently, they're balanced because your bottle's not squished or blowing up. Okay, it's staying the same. But if we took those gas particles out of the bottle by sucking on it, for example, and there were less in there, then the pressure on the outside would be greater and cause that bottle to collapse. Okay, so I want to see a video that would kind of demonstrate that. sound? Oh well, you can get the idea. So in this 55-gallon drum, they put some water, they heated it up, and now they're cooling it down. More slowly, right? But the particles on the outside, they didn't really change. The particles on the inside started to move more slowly, so there was less pressure on the inside, but still a lot of pressure on the outside, and so it caused that can to crush. Where's those sound?
Today I'm at the University of Sydney with Dr. Phil, and we're talking about the pressure that all of us are under.
You are under a lot of pressure, probably 10,000 kilograms.
10,000 kilograms is pressing in on my whole body.
All from all sides.
Where does all this pressure come from?
It's from the air.
That looks like a dance move.
I'm lifting 10,000 kilograms.
You're lifting the air. Well, how much air is there above us?
Oh, about 20 kilometers or so. So you're at the bottom of an ocean of air.
So essentially the weight of the air is squishing me in.
That's right.
And I know all of us. You too.
And me too.
Wow. You seem to be holding up rather well, though.
Thank you, thank you.
How do you do it? What
Well,
is
I've got a special trick.
Uh-huh.
I've got the same amount of pressure inside me.
Okay. So since the pressure is equal inside and outside of you, you're in equilibrium and there's no sort of crushing or expansion.
No, that's right.
Okay. Well, most people, I think, don't recognize the pressure that they're under,
Yeah,
at least due to the atmosphere.
that's right.
How can we demonstrate that the atmosphere is exerting this huge pressure on everyone?
The best thing to do is to scoop out their insides, and then there'll be no pressure on the inside, and then they'll be
Crushed by the atmosphere.
by the atmosphere.
And that will be a rather clear demonstration
Exactly.
of the power of the atmosphere.
Exactly.
But let's say we didn't want to kill anyone. How can we demonstrate this in, say, a lab?
Well, we could take a model of a person.
And this drum is meant to be a model of a person.
That's correct. Yeah.
Okay. And so what are we going to do with it?
So what we're going to do
Yeah, go
is
ahead.
we're going to put some water in here.
Why don't we go ahead and do it?
Okay. Let's do it. It's heating up.
So we've got some water in the drum, and we're heating it up on this little gas stove here.
That's right.
Okay. And what is that doing for us?
So the water will heat up and begin to boil. So it'll turn from liquid into a vapor. That vapor will push out some of the air.
Okay, so basically we're going to remove the air from inside the drum and replace it with water vapor?
That's right.
Okay.
Okay. Then once we're sure that it's pretty much emptied of air, we put the stopper in
Mm-hmm.
and cool it back down again.
Okay, so that's going to condense the water vapor.
That's right.
And so what does that do to the pressure inside the drum?
It'll become much smaller.
Okay, and then we're going to be able to see what the atmosphere does when there's no pressure on the inside pushing down.
Exactly.
All right, well, I look forward to that.
All right.
So how long do we have to wait for this to boil and get all sorted?
Couple of minutes.
Mm-hmm. Should we do a little time lapse effect?
Let's do that.
All right.
Okay, looks like we're boiling away furiously here.
All right.
Pretty good. So it's about time to perform the experiment.
Let's do it.
It might be a bit dramatic, so I'm going to chuck on a bit of gear.
Safety glasses, always important.
Yeah,
And safety gloves to avoid burning your hands on this very hot drum.
that's right. Now, you might want to put those on.
I will.
You might want to stand back a bit because it's a little bit dramatic what happens.
All right, let's do it.
To there. Alright, so that water's turning back into water vapor. Oh my god.
Right, so there is constantly pressure all around us, pushing down on us. And this pressure can change with the weather. Okay, so you may hear the weatherman say there's a high pressure system moving in, or a low pressure system moving in. Most of us do not notice these changes in pressure. But people who have really bad arthritis, or maybe like bad knees or something, they will recognize the change in pressure. People who live on the equator don't really experience much change in pressure because it's just kind of like sunny there all the time. They don't have much weather change. So when people adopt children from those areas of the world and bring them to America, those children can have a really hard time when the pressure changes. And so they'll notice them, kind of acting crazy because they feel really weird about the pressure changing. Their body's not used to that. This is how we measure the pressure in the atmosphere on a daily basis using this instrument called a barometer. So the pressure from the atmosphere is pushing down on this liquid, and it causes it to go up into this tube. If the pressure is high, it'll cause it to rise more in the tube, and if the pressure is lower, then it won't push as much, and so it won't rise as much in the tube. And so that's how we measure pressure in the air using the barometer. Right? Another factor that we have with gases is their temperature. Now, the science definition of temperature is the average kinetic energy of the atoms. The average kinetic energy of the atom. And the reason we use the Kelvin temperature scale, which hopefully you saw that yesterday, that capital K, is because when the kinetic energy changes, the Kelvin temperature changes by exactly the same factor. So if the kinetic energy doubles, then the Kelvin temperature also doubles. But that's not true for Celsius and not true for Fahrenheit. Anybody remember how to get to Kelvin temperature? Very good. So Kelvin is equal to Celsius plus 273. And there are no zeros in Kelvin, and that will be the temperature that we use in every single problem that we'll do in this section. When we talk about kinetic energy, we're talking about the energy of motion. And gas molecules have three kinds of motion. They have translational motion, which is the motion of moving from one place to another. Translational, one place to another, and they move in straight lines. They also rotate and vibrate. So they have three different types of kinetic energy, but this is where most of the energy is, in their movement from one place to another. So most of their kinetic energy is that movement energy. So when the temperature goes up, it's going to cause them to move from one place to another faster, which causes them to hit the walls more often, which makes the pressure go up. When a gas hits anything, the collision is what we call elastic. Okay, so this is a key vocabulary word. I'm going to circle, highlight, whatever. Elastic means no energy is lost. No energy is lost. If you take a basketball and bounce it against the wall, it's not going to come back to you with the same amount of energy. But when a gas particle hits the wall, it comes back with the same amount of energy. So the energy it had before hitting the wall is the same as after. If they run into each other, their energy before is the same as after. So if one of them is going fast and the other one slow, it may make that one slow and the other one fast, but the total energy remains the same. So if you have a set of gas particles at a certain temperature with a certain kinetic energy, they'll keep that kinetic energy. They're not going to lose it as they bounce against the walls. Right? This graph shows us the change in energy as we change the temperature. Change in energy as we change the temperature. Now, on the y-axis, we have number of particles. Let's see if I can draw on this. So everything under this curve, if you can kind of color in, shows you the particles that are at that temperature. So all these particles are at 250 Kelvin. following that? The area under this curve, all of those are at 250 degrees. Under the next curve, all of those particles are at 500, they say. All of these. Okay, and then the next one is all at 1,000. All of these particles. So which temperature has particles with the most kinetic energy? Okay. Do you see why some people would think it was 250? Because the peak is higher? Okay, but the peak just tells you that all those particles, they have low energy. But as the temperature increases, more of your particles have more energy. But you have to keep the same amount of particles, so you're just kind of spreading them out. So if you're at a high temperature, this is a really high temperature, 1,000 Kelvin, all of your particles aren't moving fast. Okay, some of them are moving fast, some of them are still kind of struggling down here, but on average, they have more energy than the 500 or the 250. Okay. So what will this look like on the test? I'll put this graph on the test, and then I'll give you A, B, C, and I'll need you to tell me which temperature goes where. Okay. So this, further to the right, these are actually moving faster because kinetic energy is on the X, and so they're further over. Even though that hump is lower, that confuses people. Okay, are you good with that plot? Expect to see that a few more times. Now we're going to talk about gas laws. So these laws are what you studied yesterday in the lab. The first one is Boyle's law, which is pressure and volume. So flip back to that graph. Pressure and volume. I think that's the last graph you did. All right, look at these two graph choices. Which of those two is your graph most similar to? Graph A or graph B? I heard A, B. B or A? B. Okay. For volume and pressure, the relationship is inverse. As the volume went up, the pressure went down. Okay, an inverse relationship. And we now know why. What causes pressure? Right. The particles hitting the walls of the container. So if the container gets smaller, they're going to hit the walls more. But if I make the container bigger, they're going to hit the walls less. And that's why the pressure is going down. So it's an inverse relationship, and this is the equation that I use. Okay, so you see that there in your notes. Volume 1 times pressure 1, that's before you make a change, is equal to the volume times the pressure after you make the change. Now, what are the units for volume? What's the unit for volume? Milliliters? Is that what you said? Yes, that's correct. Milliliters is a unit for volume. Now, yesterday we used that ruler, right? But rulers don't actually measure volume. So that's not really a unit for volume. We just did that because there was no other way to measure the volume on the lab. What else can we use that's similar to milliliters? Liters. Okay? So here, your volume, I'm going to make this note, your volume should be in milliliters or liters as long as they match. Milliliters or liters as long as they match. Like both of them are in milliliters or both of them are in liters. But if one volume's in milliliters and the other one's in liters, we got to change them so that they match. Microliter, yeah, it could be anything as long as they match and they're volume units. Good. Pressure, there are like 7 different units for pressure. So pressure can be in ATM, which is known as an atmosphere. can be in mmHg. It's called millimeters of mercury. I'm trying to think of all of them. Torr is a unit for pressure. PSI is a unit for pressure. If you've ever filled your car tire up with air, you're measuring the PSI, okay, the pressure inside the tire. That's another unit for pressure. We may see some others. Again, it doesn't matter which one you use here as long as both the pressures are in the same unit. I will give you like a key if you need it. Here is just a representation of that volume-pressure relationship. So if you double the pressure, you half the volume. Okay, that's what it means by inverse. So if you multiply the pressure times 3, you're going to divide the volume by 3. Multiply by 4, divide by 4. Okay, that's what the inverse relationship means mathematically. And there it is graphically. So you may be asked on a test to match a graph to a relationship. So pressure-volume graph looks like that inverse curve. All right, the next relationship we want to look at is volume and temperature, and that is the second one that we did yesterday. Volume and temperature. Did it look more like graph A or graph B? Graph A, because it's what kind of relationship? Directly proportional. Okay. This is the equation that we use to relate volume and temperature. V1, your first volume, over your first temperature is equal to your second volume over your second temperature. Now, this can be made easier by cross-multiplying to get rid of this fraction. So the way I usually write this equation is V1T2, okay, just cross-multiplying, equals V2T1. If you'll start off with that equation instead, it's a lot simpler because you're getting rid of your fraction. Okay, it'll be easier to solve. Now, one key here is you have to use Kelvin. So if they give you Celsius, what are you going to do? Convert by adding 273. Or if they give you Fahrenheit? That's right, you got to go to Celsius and then change it to Kelvin. You have to use Kelvin in these calculations. Don't worry about memorizing whose name goes with what formula. Okay? That's not that important. Even though I'm sure he worked hard for that, we don't care much. Alright? Here is an example of the volume-temperature relationship. So as the temperature goes up, those particles move faster, they hit the wall more, and they push the wall out, making the volume larger. Now, they can only do this if the container can expand. So the most popular example of this would be a balloon. So this is the way a hot air balloon works. They light the flame in the middle of the little basket in the hot air balloon, and as the air heats up, the balloon expands. It's then less dense, so that's why it rises, and they can cut the flame down to allow the balloon to come down. All right, so there's that graph. The third relationship is the relationship between pressure and temperature, but instead of giving it its own equation, we have this equation that combines all three variables. Again, I'm going to make this equation simpler by cross-multiplying. Let me not use yellow. So if I cross-multiply, then T2 is going to be up here, and T1 is going to be over here, and I won't have these fractions anymore. So P1 V1 T2 equals P2 V2 T1. This is called the combined gas law because it has all your variables in one equation. What we'll do with this equation is you can actually use this equation instead of the other two. You just get rid of whatever you don't need. So let's say that the volume is held constant So if the volume didn't change, then just get rid of the volume in that example. Okay? If the temperature didn't change, get rid of the temperature. If the pressure didn't change, get rid of the pressure. Okay, so here we go with some practice problems. Take a second and grab a calculator if you don't have one. I'm going to start with this combined gas law equation. If you look on your note sheet, the next slide there is blank to allow you some room to work the problem. They started with the fractional equation, so we just cross multiply so that we don't have that fraction when we start. So a cylinder of gas is kept at a constant volume. Okay, that's a key piece of information. If the volume is constant, then I don't need volume in this equation. It's going to cancel out. The temperature increases from 24.1. So I'm going to say T1 is 24.1 degrees Celsius. 2, now T2, 326.4 degrees Celsius. If the initial pressure is 1 atmosphere, pressure 1 atmosphere, what is the final pressure in millimeters mercury? And we're looking for P2. It does ask for it in a different unit, notice. Pressure 1 is in atmospheres. They asked me for pressure 2 in a different unit, but I'll show you how to easily convert once we get there. Right, so we're just going to plug these in. So can I put this 24.1 here for T1?
No.
Why not? Good. So let's add 273 to both of these. Then we can plug in. $297. Okay, so we have P1, 1.01 atmospheres, times T2, 599.4 Kelvin, equals P2, which is unknown, times 297.1 Kelvin. Now before we do the math, did the temperature go up or down? So what should happen to the pressure? It should go up as well. So I need to just check and make sure when I get my final answer that the pressure did indeed go up. You got that? I multiplied here and then divided by that to solve for P. what unit is this in right now? Atmosphere. So it's going to match whatever you started with. And then we got to change it to millimeters mercury. That's a simple conversion. You're going to set up your fraction. You're going to put millimeters mercury on the top and atmospheres on the bottom. Now the numbers for these I will give you, okay? But for now, I'll just tell you that 1 atmosphere is 760 millimeters mercury. Okay, I'll have those on the board or on like a little paper for you. Just remember to use them if it asks you to convert. Something like that. Alright, as we click through, they'll work through the problem again. So you see they cross out the volume. They actually go ahead and solve for P2 before they put their numbers in. So they isolate their variable before they put their numbers in, whichever way you prefer. Then they plug in the numbers and solve, and they got the same thing as we did, 2.04 atmospheres, and then they did the same conversion to change it to millimeters mercury. Their answers in scientific notation, okay, but that's not a big deal. Either way is fine. All right. Next principle, Avogadro's principle. Hopefully that name sounds familiar. What did he come up with? Good. Avogadro's number. Another good review question. What is Avogadro's number? What does that represent? 1 mole. Good. Okay. Avogadro found that number actually by studying gases. So he found that equal volumes, and so some keys here, equal volumes, different gases, same temperature and pressure. So he had different gases at the same temperature and pressure. He thought they'd be different sizes, right? Because you would think that argon would be a lot bigger than helium, if you look at the periodic table. But he found that they all took up the exact same amount of space, as long as they were at the same temperature and pressure. So that's how he came up with this Avogadro's principle. Okay? That as long as the temperature and pressure are the same, it doesn't matter what the gas is. Remember yesterday you could choose heavy or light gases? It didn't matter either way. Because as long as they're at the same temperature and pressure, they're going to have the same volume, no matter what the gas is. So that was kind of a surprising finding. Now, will they weigh the same? No, right? Some gases are heavier than others, but what he found was they actually take up the exact same amount of space. He said that is his principle. Even though they have different types of gases, they all have the same number of moles and take up the same amount of space. All right, next slide. Standard temperature and pressure. That's what this STP stands for. Okay, standard temperature and pressure. You'll see that phrase used a lot. The standard temperature for a gas is 0 degrees Celsius. How many Kelvin is that? Okay, so you might want to write that below that just to keep that in mind. Whenever you see STP, they're telling you the temperature is 273. It's like a lazy way of telling you the temperature and pressure. So I'll just say a gas at STP. That means it's at 273 and the pressure is at 1. So if you have a gas at STP, 1 mole will take up 22.4 liters of space. So this right here is going to be a conversion factor. 1 mole equals 22.4 liters. So think about your mole map, how we go from grams to moles. Remember that? Okay, grams to moles, you divide by the molar mass from the periodic table. But to go from liters to moles, we can use this conversion factor. So if you have 22.4 liters, that's going to be 1 mole, which means there are Avogadro's number of gases inside. Okay, so here's an example problem. How many molecules of air are in this room? Okay, this is a question. And let's just pretend we're at STP. So what temperature are we pretending that we're at? Okay, are we at that temperature? No, we would be freezing, literally. Okay. What pressure are we at? 1. That's a pretty good estimate. Okay. 1 atmosphere of pressure. So, if the volume of the room is this, okay, they just did that part for us. Do you have that part on yours? Okay. If that's the volume of the room, how many gas molecules are in here? So here we go with our conversion. 57,200 liters times the line. Where are we going to go first from liters? To moles. Good. Because we know that 1 mole is 22.4 liters. So what's going to go on the top? 1 mole. And on the bottom? Good. 22.4 liters. Okay? So that fact becomes a new conversion factor. So liters cancel and we have moles. What did they ask me to find though? Molecules. Alright? Stephen, how do we go from moles to molecules? Okay, so what goes on the top? Good. And on the bottom? Very good. Okay, so we can do that math and figure out how many molecules are in the room. That's a comma. Okay, the answer's there on the board, so if you're not getting that, let me know. What power did you get? Yeah. As long as you got 1.5 something and it's the right power, really the power is the most important there. Alright? That conversion factor, you can only use it if you're at STP. So only if it says STP can you use that 1 mole over 22.4 liters. Alright, we're going to skip the next slide on page 3 where it says how much space do they occupy. And we're going to move on to our last equation here. So we have the combined gas law equation, the Charles law equation, and the Boyle's law equation. And now we have something called the ideal gas equation. I call this Hervner for sure. So the P stands for pressure. Now here the unit has to be specific. So it's not like it has to match like we said earlier, but it has to be in these units. So the pressure is going to be in atmospheres. The volume has to be in liters. This N stands for the number of moles. This R is what is known as a constant. So the R is that value. So you'll just plug in that number for R. This is R's units. Okay, it's not telling you to do this math. That's just the units on R. And then your temperature, of course, has to be in Kelvin. So let's look at an example here. We have an 8.5 liter tank. So what is that representing? Volume. And it's in the right unit. Good. And it is at 16.9 atmospheres. That represents our pressure, and it's already in the right unit, which is good. And 25 degrees Celsius temperature, but it needs to be in Kelvin. And they ask how many moles. So what are we solving for? In. Good. And we want to know how many moles of helium are available in this tank for making some balloons. So we have V, we have P, we have T, and we're looking for N. PV equals N R T. You can go ahead and solve for N. So how would we solve for N? How would we isolate N? Okay, dividing by RT. We now know that N equals PV over RT. Okay, now you just plug everything in. So N equals, what's my pressure? Times V, 8.5 liters, times, or divided by R. So for R, 0.0821 liters times atmospheres over mole times Kelvin. Those are the units for that. Times, what's my temperature? Good. Kelvin. Okay, before you calculate, you'll look up here at the setup for me. The reason that I put all these units on R is so that I can see what cancels. So atmospheres and atmospheres cancel, liters and liters cancel, Kelvin and Kelvin cancels, leaving me with moles. So R has all those units on there so that they will cancel except the one you're looking for. So here I have moles left. When you do your math, be sure to put your denominator in parentheses unless you're going to do it in 2 steps. Well, R, from the previous slide, R is always 0.0821. So wherever I have R, I just put that number. And then temperature was 25, so how'd I get 298? Plug that in. And then I'll multiply this. Well, it was helium. So just saying it's 5.9 moles of helium in this. So the way a helium tank works is you have a lot of gas under a lot of pressure in that tank. But then as you let out that gas into a balloon, for example, it's not under as much pressure. So the number of balloons you can make is a lot more than the size of that tank, because the gas is going to expand as you fill those balloons. So this is a reasonable size for a helium tank. The next question is, how many balloons could you fill using this tank? Okay, so moving to example 2, if all of this helium was used to fill 1.5 liter balloons, how many balloons would we end up with? How many moles did we say we had from the last problem? 5.9 what? Sorry, I thought you said like 7. Alright, so that isn't going to change. But our other parameters did change. Notice we're not at the same pressure anymore. We're not at the same temperature anymore. And we want to know how many of these balloons we could fill at this new pressure and this new temperature when we release this gas. So what we need to figure out first is the volume total, and then we can divide by 1.5 because each balloon is 1.5 to figure out how many balloons we can fill. That makes sense, that approach? Okay. This is the volume of one balloon, but I need to know how many balloons I could fill. So I'm going to solve for V. So in PV equals nRT, do I have the pressure in this problem? Yes, it is 0.99, and that's in the correct unit. Do I have moles? Okay, same moles from the previous problem because they're coming out of that tank. Do I have R? Okay, do I have T? And I need to change it to Kelvin. I'm trying to solve for V. So what would V be equal to? Good. nRT over P. All right, you solve for V, and then we'll divide by 1.5 to figure out how many balloons we can fill. Okay, are we good on the 149? Okay, so if we have 149 liters and each balloon is 1.5 liters, then we would divide to figure out how many balloons we could fill. So the answer would be 9. So that's how if you buy the helium tank at Party City, it'll tell you how many balloons it would fill. But that's only an approximation because, as you see in this equation, if you're filling balloons at a different temperature, then it's going to fill more or less balloons. And also, if you're filling balloons on the top of a mountain where there's less pressure, because remember he said all this air is above you, this sea of air. If you go up to the mountain, you have less air above you, so there's less pressure. So if the pressure goes down, you can fill more balloons up there than you could down at the beach. That's a good question. Like on up when it was that house? I don't think so. Okay, we'll stop there for today, but I need you to do, on this back page, 1 through 9. So to do these problems, you're either going to use the combined gas law equation and get rid of what you don't need, or use the ideal gas law equation. Okay, let's look at just a few of them and decide which of these equations we should use and what we're going to get rid of and anything. Okay, so on this worksheet, number 1. Hunter, if you'll read that. Yes.
Total pressure of 1.62 liter cylinder heat kept at 35 Celsius and 1.25.
Okay, so stop right there. What did they just give us in that first sentence? Volume, temperature, and pressure. So I got 3 things so far. All right, then, Cole, what happens in the next sentence?
If the volume of the cylinder drops to 0.74 liters and the temperature remains the same, what is the new pressure inside the cylinder?
Okay, so the volume drops, so now I have another volume. The temperature stays the same though. So I could take this equation and I could take out the T's, because the temperature stays the same, and then I'm solving for the new pressure. If it gives you more than one of something, you have to use this equation. Okay, so on number 1, we're going to be using this equation, but we'll take out the temperature. Okay? However, if it only gives you one of each, then you know you're using the second equation. And you can't take anything out of the second equation.